Hello everyone, my name is Ricardo and I'm here with Reshma. Today in this video, we are going to be discussing a serious vulnerability in the Linux kernel that was discovered by the Google Project Zero team. This vulnerability is involved null dereferences in the kernel. But first, let's define what a null dereference is. A null dereference occurs when a program tries to access memory that has a null or a zero value. This can happen when a program dereferences a pointer that has not been initialized or has been freed. Null dereferences can lead to crashes, but they can also be exploited by attackers to execute arbitrary code or gain elevated privileges. This is why it's important to understand how they work and how to prevent them. We'll be taking a closer look at the technical details of this vulnerability, how they can be exploited, and exploring the broader implications for system security. So let's start with the problem explanation. The Linux kernel is the core of the Linux operating system, responsible for managing hardware resources and providing services to user applications. One of the functions of this kernel is to manage memory, including the allocation and the allocation of memory for running programs. However, a vulnerability was discovered in the kernel that involves null dereferences. Let us now explain a code sample and learn about the vulnerability and its exploit. As we can see in this slide, this is a function in the Linux kernel that is responsible for printing memory usage stats for a process. It takes in two parameters, a pointer to a sequence file, which is used for outputting data to a file, and a void pointer. The function first declares some variables. Our focus will be on these two structures, mm struct and the VM area struct. So we now call show VMA header prefix to output a header for the stacks, followed by the stacks themselves using show as map, and releases any resources that were allocated. However, there is a bug in this function. If the process has no memory mapping, the mn member of the prev structure will be null, causing the pre-mm mmap VM star access to result in a null pointer dereference. So basically, the variable is used without checking if this is a null or not, which can cause a kernel oops. So now Reshma will explain what is a kernel oops and how this code can be exploited.
Thanks, Ricardo. A kernel oops is a type of error that occurs in the Linux kernel when it encounters an unexpected condition or bug that causes the kernel to abort. It's similar to a kernel panic, but it's considered less severe as it does not cause the entire system to crash. A null dereference occurs when the kernel tries to access memory that has been released or is not valid. If an attacker can trigger a null dereference, they can potentially execute arbitrary code with kernel-level privileges, which can have serious consequences for the system. To exploit the vulnerability, attackers typically use a combination of buffer overflow and code injection. Buffer overflow occurs when an attacker sends more data to a program than it expects, causing the program to write data beyond its allocated memory. This can be used to override key variables and change program behavior. Code injection involves inserting malicious code into the memory of a running program. By exploiting a null dereference vulnerability, an attacker can gain access to kernel-level memory and execute their injected code, potentially taking control of the system. To exploit this vulnerability, an attacker could leverage a null value in the priv mmap variable to trigger a kernel oops and potentially gain unauthorized access to the system. When a kernel oops occurs, the kernel prints a message to the system log that contains information about the error, including a stack trace that can be used to diagnose the cause of the problem. The message also includes information about the kernel version, CPU type, and other system details. Ricardo and I will now go over the solution to this problem.
Yes. So in order to understand how it was fixed, we can start saying that the Google Project Zero team worked with the Linux community to develop the patch for this vulnerability. The patch introduced a new mechanism called null pages in the Linux kernel. So these null pages are a special memory page that is always mapped in the kernel's address space and contains all zeros. By redirecting null dereferences to the null page, the kernel can handle these errors safely without crashing or allowing an attacker to execute arbitrary code with kernel level privileges. So this fix has been incorporated into the Linux kernel and is now widely available. So Reshma is going to show us how to fix this in the code.
Yeah. So now the solution to the problem was to introduce a check to verify that the priv mmap variable is null before using it. So this is achieved by using a conditional check. If this variable is set, we go to the VM start location in memory. Otherwise, we can go to the specially mapped null page in the Linux kernel. With this fix, the kernel oops is prevented and the possibility for an attacker to exploit this vulnerability to gain unauthorized access to the system is eliminated.
So now we can go over our conclusion. So for this case, for this vulnerability, null dereferences in the Linux kernel can pose a serious security risk, but the Google Project Zero team and the Linux community have worked together to develop a fix that addresses this vulnerability.
By redirecting null dereferences to the null page, the kernel can protect against potential attacks and keep your system safe. Moreover, they introduced an oops limit, which causes the kernel to panic if too many oopses occur. Thank you for watching this video. We hope you learned something new today.
See you next time. Thank you.